Hello, everybody. So even if there are not that many people today, maybe because of this possibly, I don't know, a holiday, but we're going to have a recording. So I suggest to hold the session as usual. Let me recall where we stopped last time. So we gave a definition, which is one of the important definitions in the course. So we have a compact connected group acting on a symplectic manifold with a Hamiltonian action. So there is a moment map, which is a map mu to the dual of the Lie algebra of G. And we say that this is a Hamiltonian G space. If the following conditions are satisfied, and I'm going to list briefly all of them. So first of all, M omega is a symplectic manifold. So the second condition is the moment map condition. So the contraction with fundamental vector fields of omega is minus d mu x. So this is the moment map condition. And that's probably one of the important equations for us. And three, there is this extra condition that we discussed quite in some detail last time, that the moment map is equivariant under the G action on the manifold and under the coadjoint action on the dual space. So this is a very, very successful definition. And here I see in the chart there is a question about exercises. I don't know, Ian, would you mind sharing the exercises?
Anton, I'm really sorry. I don't want to intrude on your lecture recording. The fact is that I didn't bring my computer with me to just now, and so it might be a technical problem. I could try to solve it, but to do it between now and the end of the lecture might be difficult. But it will be on the website. I'm really sorry.
Okay, no worries. I can.
It will be on the website.
Of course, what I can do, I can share the kind of preliminary version, right?
With the misprints.
Yeah, with some misprints, yeah.
Okay, so we can do that, yeah. Well, it's up to you, of course. That's what you want to do.
I'll try to do it right now. Let me see whether it works. So now I put it on the chart. So again, this is maybe not 100% correct. It will be slightly corrected, but I mean you now have the main part of it. So now maybe I want to start before going for a new material. So I had some homework in which I have not quite succeeded. And so there was a question, what are the abstractions for existence of symplectic or Hamiltonian S1 actions? So abstractions for symplectic or Hamiltonian S1 actions. And well, I haven't quite succeeded for two reasons. The first reason is maybe I don't know the topic well enough. And the second reason, the answer is not very easy. So let me give you the parts of the answer that I gathered. First of all, there is a part of the answer which is sort of cheap and easy. So suppose that M is a two-dimensional orientable closed manifold. So in other words, it's a surface. So it's characterized by a genus, say G. So all such two-dimensional orientable manifolds are symplectic, and symplectic form is just any area form, right? So now what about symplectic or Hamiltonian S1 actions? Well, here we kind of easily know the answer, right? If genus is equal to 0, so we have a sphere. So there are always Hamiltonian S1 actions, because you can always bring the symplectic form to be a round sphere area form, and then you take any axis, you kind of embed it into R3, you take any axis and you consider a rotation, right? So these are Hamiltonian S1 actions. Now, if genus is equal to 1, right? So these are tori. And in this case, there are many symplectic S1 actions. And we saw examples before, and they are not Hamiltonian. And now if G is bigger than 1, there are no smooth S1 actions at all. So in particular, of course, no symplectic S1 actions and no Hamiltonian S1 actions. So nothing at all. Right? It's a little bit cheapish example because here, well, there is not much to say. And so the next symplectic dimension, right? We looked at the case of compact closed manifolds of dimension 2. Now suppose the dimension equal to 4, right? So here, well, I can recommend you some reading for that. So there is a paper by Yael Cachon. Let me give you the archive reference. So it is a paper of 95. And it continues, it builds on the previous research, and it gives some kind of classification of Hamiltonian S1 actions in dimension 4. Well, classification, I think she knows how to construct all of them, but she doesn't quite know which ones are the same. I mean, there are some results in that direction, but I think they are not complete. And in particular, from this classification, it follows that such a manifold with an S1 action is always a Keller manifold. So it admits a complex structure which is in some way consistent with the symplectic structure. And then there is a big business of constructing counterexamples. So there exist many technologies of constructing examples of 4D symplectic manifolds which are not Kähler. So they clearly cannot carry Hamiltonian S1 actions. Well, so and of course it gets then more complicated. But even in dimension 4, you see it's already like a little bit of a big business. Yes, of course it was happening like 25 years ago, but still it's a kind of already a research project to figure out how it works. All right, so sorry again for partially failing with my homework, but that's what I got for you. So now let's dive again into the theory of Hamiltonian G spaces. And I would like to start with 2 examples. One example is very easy, and another one is famously, I wouldn't say it's complicated, it's cumbersome. You're going to see. Both examples are very, very important. So the first example, and it will be important for the next homework, is just the space R2. I identify it with a complex plane, C. And we consider an action over circle. And this action is given by the following formula in complex coordinates. We just consider a linear action of the circle by multiplying by phase. It's characterized by an integer n, and we assume that n is non-zero. So as before, right, we take the symplectic form. That's the standard symplectic form on C, I over 2 dz dz bar, and the fundamental vector field implementing the unit vector would be something like this: in z d over dz minus z bar d over dz bar. So that's a small exercise to show that the vector field is this. So now a simple calculation gives that if I do a substitution, I will get what? I will get I over 2 times in, and here z dz bar plus z bar dz, and in total this is minus n over 2 d of absolute value of z squared. So the conclusion is that the moment map, in this case is minus n over 2 z bar squared. Of course, in principle, I can shift it by a constant, right? In principle, so eventually I can add a constant if I want to. But for a moment, I'm happy with that choice that we have. So minus n over 2 absolute value of z squared. So let's have it like that. And here is a small remark which will be important for us very soon. So let me say that in the case of n equal to plus or minus 1, so then the action of S1 on C without the origin is free. Maybe let me just recall, what does it mean free? Free means the stabilizer of a point it is a trivial group, right? Because if you have n, for instance, equal to 2, then theta corresponding to pi, this the corresponding element of the circle would act trivially on everything. So there would be, in general, for any point, there will be a non-trivial stabilizer. But if n equal to plus or minus 1, then the action is free. And this will be important for various applications. All right, so that's the first example. And as I said, as I promised, this example is rather easy. Now, a complicated example. Well, so I take G to be equal to the unitary group, Un, and I consider M to be the cotangent bundle of G. So, and let's say we already discussed it that this bundle is actually trivial, so we can represent points there as pairs of an element of the group and an element of the dual to the Lie algebra. Let me recall that G star we can identify in this case with the space of Hermitian matrices n by n. Okay, so what is the action? In fact, there are two actions, but maybe let me first recall how the symplectic form looks like. So the standard symplectic form in different writings. So it is D of the pairing between P and the Maurer-Cartan form. Or we can also write it D, imaginary part, trace P dGg minus 1. Or let me even be more detailed, I just apply this D. So it is imaginary part of trace. And here there are two terms, dP dGg minus 1 plus P, and here will be dGg minus 1 squared, where I have used the structure equation. So, right. So maybe just as a test question, so this sign, right? Is it correct, the plus sign, or there should be minus sign? So just right. So just for you to think about it. I think that's correct, this plus sign, but just to be sure that it's okay. Right. So in fact, there are two actions. And the first action is like this. It looks somewhat complicated, but in fact, the calculations will be in some way easier for this one. So I'm acting on the left on the group element G by some group element H of Un. And at the same time, I conjugate P by the same matrix. So this is actually, in this case, this is the coadjoint action. So I claim that this is a Hamiltonian action, right? And I would like to compute the moment map. So this is a Hamiltonian action. So why is it true? So first of all, probably it's a good idea to write how the fundamental vector fields look like. And so let me write it down, and then you tell me whether you believe me. So xm of G will be x times G. Remember, these are matrices, right? So That's why it's so easy for me to write such formulas. So you see H multiplies on the left. So I need to take, so here, how I get to this result, I need to take d over dt exponential of tx g at t equals 0. And this is xg. That's how I get this result. Now, for p, the formula will be similar, and it will be xp minus px. Obviously, the minus sign, it comes from this minus sign, h to the power minus 1. And I can also write it as a matrix commutator, xp. All right. So we are now ready for a somewhat cumbersome calculation. So I compute iota of xm omega, and I make a substitution into this last expression. So let's see how it goes. It's imaginary part, trace. So here, the substitution in dp gives xp dgg minus 1 plus p. And here I make a substitution in the first copy of dgg minus 1. I get xg g minus 1 dgg minus 1. And for the second copy, I get a minus sign because I go for the second factor, and I get p dgg minus 1 xg g minus 1. So now there are many simplifications.
You forgot to put the dgg minus 1 in the first term. It's also dp, the dp term.
Sorry, yeah, let's see. I forgot. Oh, yeah, that's right. Okay, thank you. Thanks a lot. And that's probably the most important term. So this would be what? This will be minus, right? This will be, wait. Okay, so this will be minus dp times x g minus 1, right? I think the sign.
Yeah, I agree.
Yeah, I think the sign is correct. Thanks a lot. Yeah, that's the most important term. Now, what about cancellations, right? So of course we see that here gg minus 1, gg minus 1, gg minus 1, right? They cancel out. And now observe that this term is exactly compensated by these two terms. Under the trace, we can commute sinks, and so they just exactly cancel each other. So in the end, what we get is minus imaginary part trace dp times x, or I rewrite it one more time, minus d imaginary part of trace of px, or minus d of p is x. And this last formula shows that the moment map, so this is indeed a Hamiltonian action, and the moment map at the point gp is equal to plus p. Okay. Now let me torture you with one more calculation like this. Right, there is another action. And this action looks as follows. So G goes to GH minus 1, and P simply goes to P. So this is another G action or UN action on the cotangent bundle. So the corresponding Hamiltonian vector field looks like this, and xm of P is 0. So this is for all x in G. So now we can again make a substitution. Right, so this is imaginary part, trace, and oof, okay. So minus dp minus dp gx g minus 1, right? Plus
This time the two minus signs will cancel.
yeah, we'll see. Yeah. So
oh, they should already. I mean, the first term. So you've got minus gx and you've got dp dt.
Oh, right. Thank you. Thanks a lot. Yeah, I think I'm thoroughly getting lost with it, and here there would be plus minus, right? I think.
Yeah.
Okay, minus, and here gx g minus 1 dg g minus 1 and plus p dg g minus 1 gx g minus 1. All right, hopefully that's correct. And I claim that this is what? This is hopefully D, imaginary part, trace g minus 1 pg times x. So people, could this be true? Hopefully it is true. I invite you to check it. I think it looks like it's true. And so this implies that mu of GP is minus G minus 1 PG. So there are two actions, and both actions are Hamiltonian, and there are two moment maps. So so maybe we just discuss it still for one more minute. So what we have, and actually we worked it out for UN, but this is the same picture which applies for any Lie group. So you have the cotangent bundle, you have two actions, and so here we have GP points, and we have two moment maps. Usually they are called moment map left and moment map right. And I'm sorry to say, I don't know how should I call them, right? Which one is left, which one is right? So let me say that this one is equal to P. This one, let's say moment map prime, is equal to minus G minus 1 PG. And one can actually view it a bit differently. Another point of view is as follows. You can say that G cross G acts on T star G. This is because the two actions commute, right? So the two actions actually commute. G actions. Good. And so you can think that you just have a big group, the direct product of two copies, G cross G, and this group simply acts in a Hamiltonian way. And then the moment map, let me call it mu total, is simply equal to mu prime, and it equal to P minus G minus 1 PG, and it takes values in G star plus G star, which is actually the dual space of the Lie algebra of the direct product. So that's another viewpoint on that. So as I said, this example is somewhat cumbersome, but we'll see later on that this is super important. Not today, but at the next class, we're actually gonna use it, and we'll be using it in many occasions. So this is in some way some kind of master example for Hamiltonian G spaces, and it's very convenient that it has two G actions. So this is also a particular case of maybe you can look it up just on the internet. Look up for the words symplectic groupoid, and so this notion is still a big topic in research, symplectic groupoids, and this example is an easiest case of a symplectic groupoid, and basically an example from which those people doing research on that topic, they're still taking inspiration. So here we start touching current research. So another thing I wanted to mention, in the exercises, we also start touching maybe not current research, but one of our exercises is a famous research paper dating to about 25 years ago. But still, if you look at the exercise in the problem set, so the problem number 2 is so-called symplectic cutting, and that's something which, at least for me, was one of the motivation points why I wanted to do something in that field. So it's a very beautiful construction. I hope you're gonna enjoy the exercise. Right. Okay. So this was a complicated example. So now let's develop a little bit more the theorem of moment maps. And our target today is to formulate and prove our first big theorem in the course. Right. So one topic that I want to discuss, or maybe remind you, so that's the story which goes under the name of regular values, in general, of maps between manifolds. And for us, it would be important to know what are regular values of the moment map. So if we have a Hamiltonian G space, right? So let's say this is our manifold, and it's a map into a vector space, right? So this is G star, and between these two spaces, we have a moment map. So let's choose a point psi in G star, and let's say this is a fiber or pre-image of psi under the moment map, right? mu minus 1 of psi. And here, let's say we have a point M, which is sitting in the pre-image. So mu of M is equal to psi, or the same thing is. So M is sitting in the fiber of psi under the map mu. Right. Now, at this point, we can take the differential of the moment map, and it maps the tangent space to the manifold, to the tangent space to G star. But G star is a vector space, so its tangent space at any point is simply isomorphic to that space itself, right? So, and of course, the other way around, we can say that there is a dual map. I don't know whether we should denote it by star or by transpose. So it is mapping T star psi of G star to T star MM. And this space is simply isomorphic to the Lie algebra G, right? So there are those two maps. They are just whatever canonically defined. Now here is a definition. I don't know whether you probably met it in your other courses. So psi in, oh, sorry, my color code. So psi in G star is a regular value of mu if the rank of the map of the differential is equal to the dimension of G star for all points of the fiber, right? So, so you see, of course, we know that the rank of the map is bounded by the dimensions of the source space and of the target space, right? And now we are saying that we want the dimension to be always equal to the dimension of G star. In particular, of course, this means that we now consider manifolds of the dimension at least equal to the dimension of G star. Otherwise, this cannot work. And of course, this is also equivalent to the rank of the transpose map to be equal to the dimension of G star. All right. So, oops. Oh, I'm sorry. I got misplaced my pages. Yeah, but what to do? Right. So let me just add a couple of comments on this page. So here is an important fact. So if psi is a regular value, so why are we interested in regular values? So is a regular value. So then, sorry. So then the fiber, the pre-image of psi, which is sitting inside M, is a submanifold. So this is quite important for us because we don't want to, I mean, of course, we can try to also work with various singular objects, singular spaces and stuff, but we prefer to work with nice objects. And in particular, so this, this space, mu minus 1 of psi, we want it to be a submanifold, a nice, really nice subspace within M. And so that's why we're interested in regular values. And one more fact, which again, maybe you can tell me in the chat, or you can unmute yourself. So there is a famous Sard's theorem. So this is one of the main statements that you need in the beginning of differential geometry. And this theorem tells you the following, that the complement to the set of regular values, and it's also called critical values, is of Lebesgue measure 0. So in fact, most of the values of any function are regular values. Now there is one small script point here. So if the preimage of a point is empty, right, then there is nothing to verify, right? And then it's considered a regular value. So perhaps for some maps, you have lots of regular values, but all the preimages are actually empty, right? This may happen. But still, Sard's theorem tells you that if there is at least one regular value with preimage being non-empty, then you're in a good shape. So there would be lots of good points. Okay, perfect. So now let me try to create the page in the right place. Okay. So right, let me rewrite my equations and then state a proposition. So we are looking at the following piece of geometry. So we have a tangent map to mu. It maps tangent spaces to each other. So we have its transpose.
Excuse me, may I ask a question?
Sure, go ahead.
So it means you formulate it like this because it means that it can be dense. I mean, the set of regular values. If you use the Lebesgue measure, but for example, Q is everywhere dense and with the Lebesgue measure 0.
Yeah, let's say it's usually stated like that with Lebesgue measure. Of course, then if the map is smooth, then I guess what you say cannot happen, but I would need to think a bit more about it. Yeah, of course, we probably don't want something like Q, but then I think it probably depends on assumptions on your function. I think probably if the function is sufficiently smooth, what you're saying, this cannot happen. Right, that would be my preliminary judgment.
Thank you.
Right, so the cotangent map, right, it maps the cotangent fibers. So this is isomorphic to G. And I want to introduce one more element. So we have the map which derives from the action, which maps the Lie algebra to the tangent space, and it maps an element X to the value of the fundamental vector field at the point M. And so the image of the Lie algebra G, let me denote it GM of M. So these are all these are values of all fundamental vector fields at the point M. Maybe, oops, here is a picture for that. Right, so we're sitting at some point M, and here is the orbit, and here are the tangent vectors to the orbit, and they span a subspace of the tangent space. This is right. So that's the geometric picture. Now here is a proposition. And it says the following. So we take this subspace. So this is a subspace of the tangent space. And in a symplectic manifold, all tangent spaces are symplectic vector spaces. So we can take a symplectic orthogonal of it. So it is sitting in the tangent space. And this is equal to the image of the transpose map orthogonal, where this thing is sitting in the cotangent space, and then the orthogonal is sitting again in the tangent space. Right. So, but we're going to see it now in a bit more detail when we write up a proof. Right. So this is a somewhat technical lemma, but it will be crucial in the following theorem. And the following theorem is one of the big theorems of the course. So, right. So here is a proof, and the proof is more or less obvious once we understand the notions. So that's the most difficult part of it. So Gm of M omega orthogonal, what is it? So these are tangent vectors which have the following property, right? Omega of xm of M U is equal to 0 for all x in G, right? That's just the definition of omega orthogonal. Okay. So what about the other gadget that we have in the proposition? So the image of dm mu transpose orthogonal, what are they? So these are tangent vectors such that dm of mu x, so this is the image of whatever comes from the moment map evaluated at the vector u is 0 for all x in G, right? So that's this. So these are all vectors which are orthogonal under the natural pairing to all one forms that you can get from G star using the pullback with the map mu. All right, very nice. Now, of course, the moment map condition implies that omega of xm of mu is equal to minus dm mu x of u, right? So that's just the moment map condition. And now in one definition, we want the left-hand side to be 0. In the other definition, we want the right-hand side to be 0. So these conditions are clearly equivalent, right? Okay, so that's the end of the proof. Okay. So yeah, it was technical, but we'll see that it's actually very useful. And maybe before going into the theorem, jumping into this theorem, let me make a couple of remarks. So so the first remark is that the dimension of this space GM of M, right, is now equal to dimension of M minus the dimension of the symplectic orthogonal, right? That's just the general stuff about symplectic structures on vector spaces. And this is equal to dimension of M minus now dimension of the image, right? The image that we had, mu transpose orthogonal. But of course, right, now this is equal to the dimension of the image of right. So this is just by linear algebra, right? So the first equation was by symplectic linear algebra. And this is just ordinary linear algebra. And this is, of course, equal to the rank of dm mu, right? So these two things, these two dimensions are the same. In particular, if xi is a regular value, and M is a point of the fiber, so then the following thing happens, right? So then the dimension of this GM of M is simply equal to the dimension of G star, and of course equal to the dimension of G. And this also implies that this map X to X M of M from G to CMM is injective, right? So this is a linear map. We know that the dimension of the source is equal to the dimension of the image, so it's an injective map. So you see, sorry for all those technicalities. We'll see that they are very, very useful. But of course, at the moment, right, we have this proposition, which is kind of reasonably trivial, right? This is just we can say we are playing with definitions, right? Nothing else happens, and so kind of now we're going to see why we need all that, why it is of interest. So so the next topic is symplectic reduction. And now we're going to state and prove our first big theorem. So this theorem is by far the easiest one amongst three statements that we're trying to prove in this course, but it is by far the most influential and most important one. It's kind of strange, right? So we still have whatever, 25 minutes, and we'll certainly manage to formulate and prove this theorem during that time. But this theorem continues to attract a lot of attention. So of course, we now prove some kind of the most classical version of it. But about 1 month ago, I attended a conference where one of the new versions was presented, and a very interesting one. Perhaps it will be one of the exercises, maybe not for this time, but for the next time, that theorem. And there is a constant flood of modifications, generalizations, versions of this theorem. So that's one of the big theorems of the subject with zillions of applications. So what is it about? So let's say we consider a Hamiltonian G space, and we first introduce a little bit of terminology. So we're choosing psi in G star, and the stabilizer of psi, so G psi, these are elements of G such that the coadjoint action doesn't move psi. Right? So that's the stabilizer. Maybe a fact, we're probably going to return to this fact later on for more details. So, but now just for information, if G is compact and connected, then all the coadjoint stabilizers are also connected. Right. So as I say, maybe we rediscuss this fact later on, but for now, let's take it as a fact. So let's consider the fiber of psi sitting inside M. So then, obviously, or maybe not so obviously, the fiber carries an action of the stabilizer. Indeed, the moment map is equivariant, right? Right, the moment map is equivariant, and so mu of Gm is adjoint G star psi. Oh, sorry, maybe I write it in more detail, of mu of M, and this is equal to adjoint G star of psi, and this is equal to psi for G in the stabilizer, right? So we have an action. We have an action of G psi. Now, let's make the following assumption, and we discuss it in a second. So assume that the action of G psi on the fiber is free. So this is a sort of strong assumption, but for our purposes, it's probably okay. Usually people work with weaker assumptions. So let me state the following. So if we assume that psi is a regular value, so then for all points in the fiber, we have G to Gm of M injective. And we're not going to prove it, but just intuitively, this means that if there are points of G psi which are fixing the point M, those elements cannot be too close to the group unit, right? Because because in particular G psi, the map to G psi M of M is also injective. And this means that the stabilizer subgroup, now things which are fixing psi and in addition are fixing M, is discrete. And therefore it is finite. Because G psi is compact. Right. So such actions where all stabilizers are discrete, they're called locally free. But this is just a terminology. Now, why I'm making a stronger assumption? So this is because we're interested in the following space, M psi, which is by definition the pre-image divided by the action. This is called the reduced space. Level psi, whatever that means. Another notation is M /psi G. So this is simply for us. So this has also another meaning in algebraic geometry, but for us this is just a shorthand notation for the first line. If the action is free, G psi on the fiber is free, so then the reduced space is a manifold. And that's why I want to work with this case. However, there is a whole school of, or different schools of thought who are thinking about other situations. So in many cases, people are thinking that the action is locally free. So then M psi is allowed to have some kind of mild singularities. And then it's called an orbifold. So this is already some kind of big theory. And in general, M psi may have rather serious singularities. And then it's called stratified symplectic space. So This involves already rather technical and complicated definition of what that means. So there is a stratification. Each stratum is a symplectic manifold, but those strata, they fit together in some way. So, but there are already quite serious singularities. And this is also a kind of big theory, right? What kind of singularities may occur, what to do with those singularities, how to deal with them in applications. So it's a big story. But for us, so let's formulate the theorem. So the symplectic reduction theorem, it says the following. So there is a unique symplectic structure on the reduced space such that the following holds true. And here I draw famous diagram. So there is a fiber of Xi. It is sitting inside of the manifold M, and it projects to M Xi. So let me denote the projection by pi Xi and the embedding by I Xi. And so the equation which is imposed is the pullback of the two form from M descends to the reduced space. And so together they satisfy this formula. So both the formula and uniqueness important statements. And now we have 10 minutes to look at the proof. We're going to see that we have enough time. If not, we'll see. Maybe we take 5 extra minutes or we postpone. We'll see. Right. So that's one of the big theorems of the course. It's an easy theorem. Well, this happens, right? The importance is not always related to the fact that it's complicated. So it's also known as a Marsden-Weinstein reduction. So how does it work? First of all, right, we have G Xi acting on the fiber v-1 of Xi. And here there is a projection by Xi to the quotient space. Right. And if the action is free, so then this is a principal bundle for the action of this compact connected group G Xi. Right, so we have the fiber is a total space of the principal bundle, and the reduced space is the base. Right, so this is the total space, and this is the base. Right. Now, I'm not sure how, maybe you're not all very familiar with geometry of principal bundles. Let me just give you a little bit of information, right? Of course, pi star psi. So maps differential forms on the base to differential forms on the total space. And this map is injective. So, right now you may ask a question, how to characterize the forms in the image. Question, how to characterize. In the image. In fact, there is a very simple criterion. So, fact. So alpha is in the image if and only if the following conditions are satisfied. So the form is invariant under the action of the group, and the form is so-called horizontal. So for all x in G psi. So this is called invariant, and this is called horizontal. Basically now, in order to prove the existence of a two form, we need to take the restriction of omega to the level set. Sorry, I can. Right. Okay, so I can. I should take the two form, right? I should restrict it to the level set, and I should check those two conditions. So let's check those conditions. For the two form, right? Okay, well, the first condition is easily checked. We know that if the action is Hamiltonian, the two form is invariant for all, in fact, for all fundamental vector fields. So this is funny. Now it's a little bit more tricky with those contractions. Well, we should restrict it, or maybe, sorry, let me write it more properly. So I take x in G psi, and I'm taking iota xm, iota star psi omega. But now the group G psi acts on the level set, which means that the corresponding fundamental vector fields are tangent to the level set, and we can exchange the pullback with a contraction. M is tangent to the level set. All right. So now we can simply use the moment map equation. But on the level set, the moment map is simply equal to psi, right? So this is minus d psi x. But psi x is simply a constant, right? So its drum differential is equal to 0. Okay. So here is our intermediate conclusion. There is a unique omega psi to form on m psi such that phi star is equal to iota star omega. So here remains to prove two things. Right? Omega is closed. And omega is non-degenerate. And you know, people, so while the proof that omega is closed is really an easy proof, the fact that omega is non-degenerate is easy, but it requires some thinking. And I don't think like 2 minutes is a good timing for that. So I prefer to start next time with this part of the proof. And, you know, I also want to do it because it will give me an opportunity to state the theorem one more time in the beginning of the next class and talk about that theorem again, because that's a very, very important theorem. And then we're going to use it next time to various purposes. We will construct some big family of very interesting and important symplectic structures. And we'll probably also talk about toric geometry next time using symplectic reduction. I think that will be the plan next time. And I would like probably to stop for today. You know, I'm usually filling around 11 pages, and now this is our 13th page, which means that I'm probably too fast today. Sorry about that. So I wonder whether you have questions at this point. Okay, people. Yeah, if there are no questions, I will be happy to have questions about this stuff next time. Should we stop recording?